All right, let's start this episode with the convergent boundaries. And we'll start specifically with oceanic to oceanic convergence. Okay, so we're going to have two ocean plates coming together. All right, so this is going to look a lot different than what we've done so far. Even though we had convergent boundaries in our very, very first episode with the Earth's layers, we're going to zoom in on them and get a really close look this time. All right, so we're going to start about halfway up the page in the center. I'm just going to make a mark. I'm just doing the outlines right now. We'll go and fill them in a little bit. Okay, that's going to be the ocean floor on one side. Okay, so we've got one ocean plate here, and we're going to have another ocean plate coming towards it right here. So I'm going to take this one and I'm going to dive it down underneath. It's going to dive down like this. Okay, we're going to fill this in later, so we're just making the outline right now. Then it's going to come back. Remember, the ocean crust is relatively thin, so we're going to make a thin outline of the ocean crust coming back up and coming across like this. Okay, now, what happens when two ocean plates collide? We mentioned this in the very first episode, is a volcanic island arc. So we're going to make a volcano above this. It's a nice big tall pointy structure like this. Again, we're going to fill it in so we can make a few mistakes and fix them later. And this plate's going to come back up like this. Alright, so we've got our basic shape here for the ocean to ocean convergent boundary. Alright, we've got two ocean plates colliding, coming toward each other, and some of the features are already starting to take shape. Alright, we're going to go ahead and fill in some black, get it off the brush over here, because I don't need it for the next part. We'll come back and make this a little better blended here in a little bit. Alright, so underneath the ocean crust, we've got that mantle again. Okay, the hot mantle. And the very first section of that mantle is part of the lithosphere. So we're going to add it in that red. Okay, make a nice thin red layer of mantle right here. Okay, so the topmost section of the mantle and the continental plate is all part of the lithosphere. And right below the lithosphere we have the asthenosphere. Okay, so the lithosphere rides on top of the asthenosphere. Kind of just pinch that off right there. It's okay that it's all blending together here, but I'll tell you why here in a second. Okay, because what winds up happening as one ocean plate converges and dives down underneath the other, it starts to melt. Remember, it's hot in the mantle. And that melting actually causes blobs of magma to come up. So we're going to draw a plume of magma melting off of that subducting plate and coming up through the plate that's above it. So let's draw a blob of magma inside this volcano. Okay, now what's interesting is the magma that is forming because this ocean plate is melting is rich in water and silicates, and the type of magma that it creates is very, very different than the basaltic rock that the ocean crust is made of. Okay, because we've got limestone and sedimentary rocks on the ocean floor on top of it that are melting and becoming very, very buoyant lava. So it comes up and it's hot enough to melt up through the above plate and form these volcanoes. And this is how island chains like the Aleutian Islands and islands like the Galapagos. Japan is sitting on top of a ocean-to-ocean convergent boundary, and the whole country of Japan is sitting on a big volcano. Okay, so we're going to draw in our lithosphere layer here on this one. Just remember that that magma that's coming up through it is very, very different magma than what the lithosphere is made of. It's buoyant, it's different composition, silica rich, and it's a very different type of magma than what formed the ocean floor. All right. Now, of course, this is all under the ocean, so let's color that in. And this is an island, remember, so we're not going to cover it up. We're just going to make the water come over this ocean floor. Spread it on out over here. Okay, we'll make actually some division in the water this time with some darker blue as well. Alright, so we've got nice shoreline right up against this volcano. This volcanic island. Put some waves in. All right. Now there was just recently a tsunami caused by a volcanic eruption. These volcanoes, they start out underwater. And when they erupt, they can displace large amounts of water. Or where this plate subducts down underneath, it can grab onto that plate above it and it starts to pull it down like this. And I mentioned in the first video the Mariana Trench, the very deepest place in the ocean, is where a plate is pulling down on the plate above it, subducting underneath it, and pulling it down with it. So it makes this very deep ocean trench. And sometimes those plates give way, and that plate pops back up and displaces all the water that's above it, which creates and causes a tsunami. Those are easier to explain, and there are warning systems in place because when it's an earthquake that causes it, seismometers trip signals and warnings that there is a possibility of a tsunami. But the recent tsunami was not, didn't have much of a warning because it was a volcanic eruption that was not an earthquake. So the tsunamis can be caused by a bunch of different things, but they are also traceable back to plate tectonics. Okay, so plate tectonics is this universal rule or universal theory of geology, the unifying theory of geology. It puts everything together, gives us an explanation for why things are happening on the Earth's crust, on the Earth's surface, and what's happening underneath. All right, so we blended together our ocean. Remember that this is going to be labeled as an ocean trench. So the deepest places in the ocean are right there in these convergent boundaries. All right, and we've got that volcanic island above it. All right, so let's fill in the ocean crust with black so that we can make that distinction between them. Okay, now with the convergent boundary, unlike the divergent boundary where there's a mirror image on both sides, we don't have that happening, although this is old crust being subducted down underneath and into the mantle. So it's going to get recycled. So even though these volcanoes are brand new, the material that they are erupting out with is actually just recycled crust. It's recycled, remade in a new form, a new chemical structure, but it's still recycled material. The Earth doesn't waste anything. Everything gets recycled. That's why we call this part of the rock cycle, the cycle of tectonic plates, the water cycle. All these things are recycled material that the Earth is using over and over and over again. And that process is going to keep going until the mantle and the core completely cool down. Now, the Mars InSight rover just landed recently on Mars, and its whole mission is to study earthquakes on Mars. I guess they're not really earthquakes then, they're Mars quakes. But that's what it's doing there. It's looking for vibrations, seismic vibrations. And scientists think that Mars used to have plate tectonics. There's evidence for two giant plates, a northern hemisphere and a southern hemisphere plate, and some fault lines that are detectable. But they don't see actually active volcanoes anymore. So that leads scientists to believe or hypothesize that Mars does not have active plate tectonics any longer. Which makes sense. It's about a quarter of the size of Earth. It didn't take as long as Earth is taking to cool down. Okay, so its tectonic plates have stopped moving. So it'll be interesting for InSight to see what is going on. And most of the seismic vibrations that it's probably going to pick up are things due to landslides and other events like that. Alright, so I'm going to leave just a little bit of white there so we can see that break between the two plates. Alright, so this is our convergent diagram. And we're going to add the little arrows for the mantle convection. This time, the mantle convection is coming towards the juncture of these two plates. Okay, and where the slab is getting pulled down, that's where the down section of that mantle convection is going to occur. It's going to cycle down right here. Okay, so the mantle is getting cooled off and it's falling, but it's still hot enough to melt this ocean plate and have that magma rising up into the volcano that's above it. Okay, I got this melting of this oceanic plate coming up through and piercing through the plate that's above it and causing this volcano. All right. So this is oceanic to oceanic convergent boundary, which is just the first convergent boundary. Okay, so that's the end for this diagram.